Hello, everybody, and welcome to WCA Physics B. We are currently looking at Unit 2, Lesson 8 on thermodynamics. This is heat engines and efficiency. So again, just trying to help you out a little bit with some of the math, some of the concepts so that you understand what's going on in the lesson. Key terms are efficiency, entropy, which we talked about in the last lesson, first law of thermodynamics and second law of thermodynamics. And then, so the idea again behind entropy is a state of disorder. And when you look at, um, you know, there's never a situation, it says, where the bricks will assemble themselves into a house. So it's much more likely that a house will crumble and become a pile of bricks than the bricks will just spontaneously assemble themselves into the house. So according to the second law of thermodynamics, everything in the universe has a tendency to trend towards more disorder. Um, in order, you have a coffee cup that is hot, it is going to become cooler over time. It's not going to become hotter over time, right? So heat is always moved from hot to cold. That is the first law of thermodynamics. Heat is the transfer of thermal energy, remember. So that's what heat actually is. In order to gain heat, so if you wanted to heat up your cup of coffee, you have to add energy to the system to do that. It isn't going to spontaneously get hotter. A heat engine is something that uses heat to do work. So in this example, let me see if I can pop this guy out so we can see him a little bit better. But we have a hot reservoir. In other words, something that's heated, right? And we're going to use that to do some work. So an example of that might be, let's say I have, I don't know, a fire. This is my campfire wood, just FYI. And here's my fire. And I have a pot of water that is kind of hanging over the fire. And it is emitting steam. Now, normally you can't really see water vapor, but we get the idea. And so the whole concept then for the heat engine is that that can turn, say, a turbine. If this is my wheel that spins, right? So the rising steam from my heat reservoir can do work by turning a turbine. This is what happens actually in most power plants, is that steam is generated by burning coal or by using the energy from a nuclear reaction to heat water and boil water, and that moving steam turns a turbine. It turns a propeller blade. So it's doing a work on the propeller blade. It's moving a force. It's moving something of weight over a distance. It's doing work. But the majority of the heat is actually, we often say it's lost, but you have a lot of radiation, you have a lot of, you've got heat that is you're going to feel that, right? So is, this is the part that you can use to do useful work right here. But most of it is just going to be dissipated out to the cold reservoir, which is the air surrounding it here, okay? So how much of it can be used to do work is we can measure that and we can determine how efficient that machine actually is. Because the more efficient it is, the more will be used to do work. And I don't know if I can use this pen. I don't think so. My tools are on the wrong screen this time, but the more can be used to do work and the less will go into the cold reservoir. Okay? That's kind of the idea there. Now, we can represent this in a mathematical formula, right? So if we think about it, the work or the heat that you're bringing in from the cold reservoir or the hot reservoir, okay, should be equal to the work that's done plus whatever energy is left over to go to the cold reservoir, right? So this is all, the top part is all of the heat available or all of the thermal energy. And this side here is how it's divvied up. So if I want to determine how much work is done, I can just move this around a little bit. And I can say, if I take the total amount that I start with and I subtract what makes its way to the cold reservoir, right? What's left over is just the stuff that does work. And that's what the formula is here. So that's the work done by the heat engine. And then we can say, well, how efficient is our engine? Well, our engine is the efficiency, which we use, that's not the letter. Okay. Is equal to the work that is done divided by the total amount that we started with, which is Q sub H, right? It's a ratio. And it's going to be a percentage. So whatever the ratio ends up being, you convert it to the percentage by multiplying by 100. So we could just basically say this times 100 is going to give you your percent efficiency. Or they've done it a little differently. Hang on a second. I'm going to take back what I just said here, because if I take, oh, so they're elaborating on this, right? So let's get this in terms without W. So that's still what I said is true. But also, because let's say I don't know how much work is done, but I just know Q sub H and Q sub C, that's all I know, right? I can also rewrite this. So I'm going to take this back a little bit. So this is true. And another way of expressing this is, I'm just going to write it the way they have it at the bottom, 1 minus Q sub C over Q sub H. Okay, because when you look at this, they're saying, well, if work is equal to Q sub H minus Q sub C, we can substitute that in for here, and then we can simplify. So there's two different ways you can solve for efficiency. These are both efficiency. Okay. So that is basically the end of the math content and all of the concepts in this lesson. Let me know if you have any questions, and we'll catch you in the next one.